simply by changing that approach and going to solid carbide tooling, our cycle times that we're able to achieve were 100 times what we were achieving with the insert cutters.
This kind of valve goes into all kinds of marine vessels, and it is a procurement challenge. Very long lead times at the foundries, which are international, and there is the capacity in the New South Wales supply chain to actually supply this kind of component. So formed a great demonstrator for us to work on.
Today we're here at the AMRF to talk about the sub-valve demonstrator project. We've got Ben and Mitch here. Would you like to tell us a little about yourself?
Go Mitch.
I'm Mitch. I'm the senior machinist at the AMRF. I'm responsible for the operation and maintenance of all the machines here in the background that you see. I work pretty closely with the precision machining department as well, in working with them with fixtures, tooling and programming to be able to then run parts like the sub-valves.
Thanks. Ben Kitcher, Executive Director for the AMRF. Been with the program since day one. So since this was a twinkle in the eye, all the way through to where we are today, obviously sat in the AMRF and planning the next stage. Probably more importantly than that though, a machinist at heart, if not by trade. Once upon a time. But you know, this project is close to my heart, employs a lot of technologies, demonstrates capabilities that the AMRF is all about. So looking forward to talking more about it.
Fantastic. So tell us a little bit about how this project came about.
All right. So as we were gearing up to launch the AMRF, we understood there are certain things that we want to be able to demonstrate to manufacturers and do it in a way which is understandable, accessible. We can actually be open about the outcomes and show what the art of the possible is before we get into some of those customer specific projects where actually there's confidentiality involved. We need to be sensitive around that data. And one of the opportunities that came to the forefront was actually working on a problem that was proposed to us by the Navy. And the Navy had articulated the timescales involved in the procurement of some of the parts that, you know, obviously are hugely important to keeping vessels out at sea, but come associated with these gigantic lead times. And we looked at that and said, well, with the right material inputs, with the right quality systems in place, and the right assurances around the processes you're running, you could actually machine these components. So you can take a different manufacturing approach to a component that could massively accelerate the rate at which those things can be procured. And probably most importantly, you could actually engage a local supply chain in that procurement rather than looking at traditional international supply chains for your parts. So we looked at this and we identified that one key component that kind of exhibited a lot of the challenges, a lot of the features, and critically one of the procurement challenges was a valve. And this kind of valve goes into all kinds of marine vessels, and it is a procurement challenge. Very long lead times at the foundries, which are international, and there is the capacity in the New South Wales supply chain to actually supply this kind of component. So formed a great demonstrator for us to work on.
Very interesting. And tell me about the material that was selected for this project.
Okay, so the material is as it would be in a marine application. So, you know, this marine application, you have to have corrosion resistance. Weight is a consideration, but you're not looking for the lightest weight alloy overall. So you're driven down into those corrosion resistant alloys, and there are very specific ones that are used in these types of applications. They're typically a casting alloy that you'd use, and in this case, a duplex stainless steel is the OEM spec material that would go into this application. So that is exactly what's gone into this project. We're working with a billet, and Mitch will be able to tell you if it's a forged billet. I believe it is.
Yep.
But a forged billet of duplex stainless steel is an input to the project, which we know is a challenge from the outset, but that's what we're here to solve.
What are some of the challenges of working with duplex?
So some of the challenges that we faced with this particular part was just originally was just the size of the billet. So we started out with a billet that was 450 mil diameter by 600 mil long and weighed about 800 kilos. To put it in perspective, when the part is finished machined, it's going to weigh approximately 130 kilos. So there's a lot of material that has to come out of it. So the first challenge that we faced was how do we hold that and how do we fixture that in our machines to begin with? And then also the properties of duplex. It's a very gummy material, but it's also a very tough material. So it really puts your tools to work, and the way that you enter into the material, the way that you exit the material, and how you're actually engaged in the material with that cutter all plays a part in how long your tools are going to last and how well the machine's going to work and how well the chips are going to come off the part. So we found during the initial stages of machining, the more economical way of attacking this would be to use inserted tip cutters. So the benefit that you get out of that is you're using a very small amount of carbide, which ends up being cheaper in the long run. The problem with that though is we were only getting very small cycle times out of it. So the length of time that we could actually cut with those inserted cutters was very small, which meant we had to have someone stationed at the machine constantly to be able to change those inserts out. From that, we sort of looked at, all right, well, that was the economical way that we would look at it. What is the more optimized way that we'd look at it? And that's where we sort of broached into solid carbide tooling. Simply by changing that approach and going to solid carbide tooling, our cycle times that we're able to achieve were 100 times what we were achieving with the insert cutters. So we went from somewhere about 8 to 15 minutes with an insert cutter to 8 hours, 9 hours, 10 hours with solid carbide cutter. This helped us greatly because we were able to then leave the machine unattended. So we're able to run it during the day, program it during the day, set it up for a night run and let it run overnight. Doing that though as well also brought its own challenges. So we had an incident where a tool actually broke in the middle of the night. But we looked at that and how can we avoid that from happening, and we were able to implement processes on the machine using load monitoring and tool wear detection on the machine. And that was able to then help us, if there was a problem in the middle of the night, the machine would stop and we wouldn't cause any more damage to the machine or the part itself. So.
It's quite impressive how you're able to overcome some of those challenges within the process.
Yeah.
Talk to me about how important getting the right team together is and how you tapped into different expertise across the team to complete this project.
Yeah.
So clearly I had nothing to do with this because we're talking about expertise. That's long gone. You know, you do need different perspectives, and what Mitch shows is actually the really kind of tacit understanding of the cutting process on the machine, the interaction of the machine tool, the spindle, the tool, the material, and the chip that comes off. That's invaluable. You can't do this from a textbook. You need to be informed by the actual process that's happening on the ground. So you know, Mitch has been able to bring that to the team. We've also got then the support of Luke and Ian. And Luke and Ian have been coming at this really supporting from a process planning, programming point of view predominantly. And again, getting tools and systems bedded down, because you know this project isn't just about the demonstration. We've also got to consider that every single system, process, tool, software, machine in this environment and entering into this project is brand new and unproven at this stage. So what they've been able to do is actually build these systems as we go and make sure everything integrates. So the point that Mitch raises around managing risk whilst running lights out on a machine is actually one of those things which typically as a machinist you might approach, you know, several years into the relationship you have with a machine or a product. We were doing this in week 2, week 3 of actually being in this building and using these machines. Now, the driver for that in our instance was actually to get ready for an event, a really important event in the opening of this first building. But what it shows you is by bringing that team together and having those different skills that you're able to accelerate the rate at which you overcome challenges, which are just pure productivity gain.
So you're saying, you know, one of the biggest benefits of working with the AMRF is having all of those different expertise and machines all under the one roof.
Absolutely, and again, I discount myself from that. But you know, that's absolutely right. Actually, the machines are the demonstration or the outcome, and the parts of the outcome of what we're really demonstrating here, which is those inputs leading to a process to achieve something which is at the cutting edge in terms of the productivity, the economic or financial outcomes of a certain process being applied. Mitch talking there about the value in moving solid carbide tools. Actually, that's a balanced equation that helps you understand what investments do I need to make to get the best productivity and profitability out of this particular machining challenge. And so that's what the project is about, demonstrating. And then it's also about what it is we're here to do. It's to help manufacturers understand, break those down, do it in an accelerated way, but then be able to go and apply that directly into their own manufacturing facility.
And just on that as well, I think also working very closely with our suppliers that we have here at the AMRF. So, we use Hypermill programming software, and getting the verification software and the virtual machine set up was a timely task. So we were having to work very closely in response with our supplier for Hypermill OpenMind in trying to get that sorted so that we could hit our timeframes that we were after. Also all the way down to just the fixturing of it, working with our suppliers on best practices and what is available in the market for the task that we're trying to achieve in fixturing and tooling and that as well. So having that close relationship with suppliers really helps us as well.
So besides moving to solid carbide, what are some of the other tooling optimization lessons that you learned along the way?
Yeah, so the move to solid carbide also brings a range of different tooling that is available. You're talking different flute counts, different tool nose radii, different helix angles. So working really closely with our suppliers and also testing the tooling as well really helped to sort of narrow down what we were sort of after with the tooling. So very early on, we found that a really small nose radius, they come standard about 0.8 to 1 mil nose radius. We weren't getting the cycle time that we were after out of that. We found the critical failure point was the nose radius area. It was just too sharp of a geometry. So working with our suppliers, we found larger nose radius, up to 2 mil and 4 mil nose radius on a 25 mil cutter. And that's what we found was the sweet spot, and we weren't getting a critical failure at the tool nose. We're actually starting to see the failure across the entire end mill. So we knew that the end mill was actually withstanding the cut and holding into the cut. Broaching more onto the different geometries of the tool, so tool flute count and helix angle, we did try a variety of 3, 4, 5, even up to 10 flute count. We found that the larger flute count that we went to, obviously you have your limitations in being able to take a deeper cut. So while we were still able to achieve the 8-hour cycle time with the carbide, we weren't actually removing as much material because we weren't able to get that cut out and that material out of there. So we actually opted for a very simple geometry, which is a standard helix angle with a four flute geometry, just with that larger nose radius, and that seemed to work for us. We were able to get the right cubic centimeters per minute out of the material, and we were able to get the longevity in the tool as well, and the tool life that we're after.
As well as being able to achieve that metal removal rate, or actually to achieve that metal removal rate, going to a larger nose radius actually has its own benefits, right? You can actually exploit that in terms of how you program the speeds and feeds that you use, because the nose radius gives you what's called a chip thinning effect. So you're not actually taking a full solid 100 micron or 200 micron feed per tooth. Actually, you're taking an average across the length of that chip, which is caused by having a nose radius on your tool. So this is another one of those things where you say, I'm making a trade-off, I'm having to make certain selections, but it opens new doors and avenues for you to then exploit, and using your programming strategy that then you can apply to the part.
Tell me about machining the inside of the valve.
Yeah, so machining the inside brought about its own challenges on top of what we've already discussed as well. You have to think about it. What I'm showing here is an open model. When we're actually working on it on the machine, it's obviously all fully enclosed up. So the only way to access the inside is through the openings that you see here. Not only that, also the complex curves and geometries that are in here as well as the depths that we actually have to achieve, really pushed our suppliers and our team as well on what was available on the market, and if it wasn't available, is it something that we maybe had to design and get custom made? Luckily enough, we found a combination of rigid tool holding with silent bar application, as well as the solid carbide heads, or the solid carbide that we were talking about. And that was able to give us the depths that we were able to achieve then to be able to get in here. It was really a combination of trial and error though, so what worked and what didn't work. So while we had the challenges on the outside, and we found from indexable tooling to solid carbide tooling, that didn't necessarily work for the inside of it. So we're back to the drawing board on that basically as well.
And how did you overcome that?
So we overcome that by pretty much trial and error. So we went back to what do we know? So we went back to insertable end mills and insertable cutters, and once again that worked, no problem, but cycle time was an issue there. So from there we were able to go into, all right, we know solid carbide worked well on the outside, trying to get solid carbide that works through the entire depth that we needed to get would require a custom tool. So what else was on the market that we could probably look at instead? That's where we sort of went down the route of the silent bar application with the solid carbide heads on top of those. So as we were able to machine this out, those solid carbide heads would wear, and we're able to just to change that little head on the bottom of it and pretty much keep the process rolling. And we're able to get the cycle time that we needed. But we found that on the outside, high feed cutters were not really working for us. They were causing too much vibration, and they were causing too much chatter issues or surface finish issues on the outside. But actually, high feed cutters on the inside seemed to work really well, so we're able to go down that road instead.
So machining dynamics is a huge part of tackling a component like this, both for the tools, those long length to diameter ratio tools necessary to get into this kind of component, but also the part itself. When it sits on the machine, its dynamic response to inputs such as your tool is changing with every cut that you take. The part is always changing and evolving. So one of the technologies and capabilities we're in the process of applying here is dynamic analysis. So we can actually characterize and optimize the vibration of the tool, the machine, the part, to work together to find those parameters that give you the productivity.
So tell us about the machine you chose for this project.
Yeah, pretty important piece of the puzzle, right, is actually what platform, what tool you use to tackle a part like this. So the nature of the input material that Mitch talked about, heavy, big, difficult to hold, lends itself to something with a pallet where you can actually use gravity in your favor to mount a component like this. So something with a horizontal spindle orientation is always going to be helpful. The DMU 80 that we've used from DMG Mori on this project gives us exactly that, but also of course the 5-axis capabilities. Now, when we look at broadly across the AMRF what it is we're implementing here, we're looking for ultimate flexibility. We don't know which kind of product or challenge the users of the AMRF are going to face on a day-to-day basis. So these machines have all been specified with that in mind. The DMU gives us that kind of ability to handle big, heavy parts, but also the agility to prove or demonstrate 5-axis tool paths around it. A machine like the NT 4250 is the kind of machine where actually a hybrid turning machining process really lends itself to that kind of platform. The Hermle C250 is the kind of machine where actually automation, a smaller component, really high speed, rapid turnaround parts are again very well suited. But across the board, these are machines that have a high number of options to provide that flexibility for different types of components like this.
Just to also add to that, one of the key benefits that we have with the DMU 80 is actually the spindle size. So HSK 100 tooling lent itself to the fact that we weren't going to run into any issues with tool holder rigidity or spindle rigidity, and that all of the issues that we were going to possibly encounter were going to come from a tooling based side of the issue.
Yeah.
Yeah.
And it's really important as well to note that it's a direct drive spindle on this machine, so there's no geared heads involved in giving you that 5-axis articulation. very, very helpful in terms of managing your accessibility, but also again the dynamic effects of when you're working with these tools. Those geared spindles or geared arrangements can sometimes introduce secondary effects in the dynamics of the machining.
So it sounds like there's a great amount of flexibility that you have between the different machines to tackle any sort of problem that is brought to you at the AMRF.
Yeah, that's the intention.
Thanks for joining us today, telling us a little bit more about this project. If you have any further questions that you want answered, just leave a comment below or get in touch.